welcome to the lecture series of network theory. We have already started learning the application of different important theorems in DC circuits. Today I will discuss about the application of superposition theorem, which is another important theorem. Superposition theorem is applied in electrical circuits where we have two or more than two energy sources, maybe voltage sources or current sources, or maybe both. So first we will see what this theorem states, and then by applying how we can simplify electrical networks, that we also see next. The superposition theorem states that in any linear bilateral network containing two or more than two independent energy sources, it may be current source or voltage source or maybe combination of both, acting simultaneously, the resultant current through or voltage across any branch is the algebraic sum of currents or voltages caused by each independent source acting alone, replacing all other independent sources by their respective internal resistances. Now we will understand the statement of this theorem by an electrical circuit. Here in this electrical circuit or network, we can see here that we have three resistors having their resistance values R1, R2 and R3 simultaneously respectively, and there are two energy independent sources, one current source and one voltage source, which are acting simultaneously. Now as per this theorem, suppose if we want to find out the current value through this resistor R3, and if that current value is I, then as per this theorem what it says is we will consider one independent source at a time. Suppose in the first step we want to consider the voltage source, then we will deactivate the current source from that network. So what is the rule of deactivation is that I will discuss later on. So first we will consider one independent energy source at a time, and that will act in that circuit alone, and we will deactivate all other independent energy sources. Then we will find out that what is the current value that is flowing through that concerned resistor or concerned path because of that independent energy source. And then in the following steps we will consider other energy sources which will be acting alone, and in that step we will deactivate all other independent energy sources. So since in this circuit we have one voltage source and one current source, so in the first step we are considering here only the voltage source, and we have deactivated the current source, and we are finding out that how much current is flowing through this resistor R3 because of this voltage source. Then in the following step what we will do is we will consider the current source and we will deactivate the voltage source, and then we will see separately that when the current source is acting alone, then how much current is flowing through that concerned resistor R3. And then what we will do, we will algebraically add those two currents. Here the currents are flowing in the same direction, so we will be adding those two currents, and that will be the net current which is flowing through this resistor R3 when both the energy sources, independent energy sources, are acting simultaneously. So this is what superposition theorem says. Now we will see that what are the steps that are followed when we apply superposition theorem in an electrical network to simplify that. So in the first step what we do is we retain one independent energy source, whether it is voltage source or current source, at a time in the circuit along with all other dependent sources. So as I said that the electrical network along with two or more than two independent sources, it may have dependent source also, or it may not have. So if the electrical network has any dependent source, then we will retain that dependent source along with a single independent energy source in the circuit at a time. And what we will do, we will deactivate all other independent sources. So in the first step we will consider or we will retain only one independent energy source in the circuit along with all other dependent sources if the circuit has any, and we will deactivate all other independent sources in that circuit by replacing them with their respective internal resistance values. Now what we do here, we replace all other independent sources by their internal resistance values. So the circuit, what we have seen here, that when we considered voltage, we deactivated this current source. So with this current source, there, since this current source was an ideal current source, so this current source didn't have any resistance which is connected in parallel with that current source. So simply we deactivated the energy part. That means we opened the terminals across which the current source was connected. So when the current source is ideal, then we just remove that current source and we make those two terminals across which the current source is connected open. So it creates an open path across those terminals where the current source was connected. So if it is an ideal current source, otherwise with that current source, if suppose there was any resistor which was connected in parallel, so we'll keep that resistor in the circuit and we will deactivate only the energy part. We will keep the resistance part. Now that's what it is written here, that if the current source is ideal, then we will remove that source and we'll keep the respective terminals open. But if the current source is not ideal, then with that current source there will be a resistor which will be connected in parallel. So we will deactivate the energy part and we will keep the resistance part in the circuit. Otherwise it will create a open circuit across those terminals if it is an ideal current source. And in case of voltage source, what we do, in case of voltage source, if suppose if it is not an ideal voltage source, then along with this voltage source there will be a resistor which will be connected in series. So suppose between these two terminals where this voltage source is connected, if it is an not ideal voltage source, then there will be a resistor connected in series. So we will deactivate the voltage part, the energy part, and we'll keep the resistance in that circuit. So in place of the voltage source, we will just short that path and we will keep the resistance. So if it is an ideal voltage source, then we will simply short that path in place of voltage source. And if it is not an ideal voltage source, then there will be a resistor which will be connected in series with that voltage source. So in that case, we will keep the resistance value and we will ignore the or deactivate the voltage part. Now in this case, since between these two terminals only voltage source is connected, so that was taken as an ideal voltage source. So these two terminals was shorted. So this is the role how we deactivate an ideal energy source, be it current source or voltage source. So in the first step, we will consider one independent energy source at a time and we will deactivate all other energy sources, but we will keep the independent sources if there is any. Now in the next step, what we will do, we will find out the concerned parameters. Like if we want to find out the current value through any concerned branch or through all the branches that the circuit has, then we will find out all the current values because of that independent energy source that we are considering at that moment. And if suppose we want to find out the voltage drop across every branch in that circuit or across any concerned branch, then we will do that. We will find out that because of that independent energy source that we are considering at that moment. And to do that, to find out the current value or voltage value, whatever, we will apply the KVL, KCL or any other relevant theory or concept that we know. And then after finding out the concerned parameter, what we will do in the next step, again we will repeat the step 1 and step 2, and this time this will be for other independent sources. So if suppose we have multiple sources, then for the first source it is done, the step 1 and step 2 has been they have been executed. Then in the step 3, what we will do, we will now this time consider some other independent energy source and we will deactivate all other energy sources from that network, and the rule is same. And if the circuit has dependent sources, then we will keep them. And then we will find out the concerned voltage or current that we want to find out. So we will do that for the second source. Then if there are some other energy sources, independent energy sources, then we will repeat the step 1 and step 2. So for the third source, this time we will consider the third source and we will deactivate all other independent energy sources. So this way we will repeat the step 1 and step 2 for all the energy independent energy sources one at a time. And then when this consideration is complete, then what we will do, we will algebraically add all the currents that we have found out because of all those independent energy sources, if it is current. Otherwise, if you want to find out the voltage drop across any concerned branch, then we will add all those individual voltage values that we have found out for all those independent sources. Now here I am saying that algebraically we will add all those current values and voltage values. So what does it mean algebraically? Now suppose through any branch, if we see that the individual currents that we have found out, they are not if they are flowing in the same direction, then we'll simply add all those values. But if we see that all those currents are not flowing in the same direction, so what current direction can be of two types: either it will flow in clockwise direction or it will flow in anti-clockwise direction. So we will choose any of the directions as positive. It may be clockwise or anti-clockwise, and for the other direction that we will take as negative. So when we are choosing clockwise direction as positive, then if the other current or currents that are flowing in opposite direction, means in anti-clockwise direction, those current values will be taken as negative, and vice versa. So suppose if there are two current values which are flowing in this direction, I1 and I2, then the net current I will be simply I1 plus I2. Even the currents, if they are flowing in the opposite direction but both the directions are same, in that case also I will be I1 plus I2. But if both the currents are flowing in opposite direction, say this is I1 and this is I2, then in that case the I will be, if we choose the direction of I1 as positive, then direction of I2 will be taken as negative. In that case the net current will be I1 minus I2. In case of voltage values also, if suppose if we see that the polarity of all the voltage values that we have found out across any branch, if they are same, then simply we will add them. Otherwise, if we see that the polarities are different, then suppose one voltage value, the polarity of one voltage value is like this: here it is positive, here it is negative. And if suppose for the other voltage value, if this is again, this is the positive terminal and this is negative terminal, then net voltage V will be simply V1 plus V2. But if we see that V1 is like this, this is positive terminal, this is negative terminal, and V2 is like this is negative and this is positive terminal, then in that case, if V1 we take as reference, then the net voltage V will be, in that case, this will be positive voltage V1. And since for V2 the polarity is opposite to V1, then in that case the value of V2 will be taken as negative. So net voltage will be, in that case, V1 minus V2. So in the last step, when we will find out the net current value or net voltage value. So in case of current, we have to consider the direction of the current, and when we are finding out the net voltage, we have to consider the polarity of the all the voltage values that we have found out for all the independent sources. Now we will solve a few numericals by applying superposition theorem, and this theorem will be more clear by these numericals. So in this circuit, what we want to find out here is the current value through this 1 ohm resistor by applying the superposition theorem. Now this is the 1 ohm resistor through which we want to find out the current value. And in this electrical network, we have some other resistors and they are having their own values. And in this network, as we can see, we have two independent energy sources: one current source having value 4 ampere and one voltage source between these 2 points having value 6 volt. And in this circuit, we don't have any dependent source. So how to apply superposition theorem and how to find out the current value, we'll see step by step. This circuit has been redrawn to clearly understand their connection, the connection between among all the components in that network. So here the current source, as it was connected between these 2 points, it is redrawn that way, and then this resistor. And as we can see in the original circuit, that between this point and this point is also same as this and this point. That means we can say that between this and this point, this resistor is connected. So that way this 1 ohm resistor has been redrawn here, and it is been shown here. So this is the 1 ohm resistor or concerned resistor through which we want to find out the current. Now between this point and this point, this 2 ohm resistor was connected in the original circuit. So this is basically the point A and this was the point B. So in the modified circuit, this is A, this is B, and suppose if this was C, so between A and C this 2 ohm resistor has been connected in the modified circuit, and between C and this B this voltage source was connected. So likewise the this between this point C and point B the voltage source is also connected here, and 1 ohm has already been drawn, and the rest is this 2 ohm resistor which was connected in the original circuit between point C and point B. So here in the modified circuit also it is connected between point C and here point B. Now we will apply superposition theorem step by step in the modified circuit. So in the first step, what we have done here, we have considered the current source or 4 ampere current source, and we have deactivated the voltage source. Since 6 volt voltage source is an ideal voltage source, so we have deactivated this voltage source by shorting the path between these two terminals C and B. Now we will simplify this circuit and we will find out the current value through this 1 ohm resistor. Suppose if this current is I1, then how to simplify? As you can see here, we have a parallel path between this 2 ohm resistor and this shorted path. So the equivalent resistance of this parallel network, it will be, suppose if that value is R1, then it will be, for a shorted path we know the resistance value is 0, so it will be 0 multiplied by 2, 0 plus 2, and that will be 0 ohm. So in case of a parallel path, if one of the branches is simply a shorted path, then the net resistance or equivalent resistance of that parallel connection will be 0. That means again the shorted path only. Instead of this parallel path, what we can say here, that since the equivalent resistance is also has the value 0 ohm, that means shorted path only, so we can neglect this resistance and the equivalent resistance will be simply this path. Now we can say that between this point A and B, if we consider the right hand side of this network, then simply between A and B we will have, at this side we'll have this 2 ohm resistor, and all other components that we had in the original circuit, they will be as it is. Now we will redraw the modified circuit. So in the modified circuit we have this current source, we have this 2 ohm resistor, and we have this concerned resistor through which we want to find out the current value, and on the right side we have only 2 ohm resistor. Now we can see here that here these three resistors are connected in parallel with each other. With that there is a current source 4 amperes. So what we will do next, we will simplify this parallel connection between this 2 ohm resistor and this 2 ohm resistor. And if we simplify that, then again if we assume that the parallel resistance is R2, then it will be between these two resistors, so it will be 2 multiplied by 2 divided by 2 plus 2, so it will be 1 ohm. And again, since both the resistors are having the same value, so equivalent resistance will be half of their each value. That also has been discussed in earlier class. So the equivalent resistance will be 1 ohm, and the modified circuit now will look like as if we have a current source having value 4 ampere, and then the equivalent resistance which has value 1 ohm, and then the concerned resistance which also has the value 1 ohm. Now we will find out the current value through this 1 ohm resistor. Now since in this parallel path both the resistors have the same value 1 ohm, so the current here which has the value 4 ampere, that will be divided at this point into two equal parts. So through this the current that will be flowing, that will be 2 ampere. since their resistance values are equal. Now if their values are not equal, then we can apply the current division rule, and for that the current value how we can find out is the opposite resistance, which has the value 1 ampere, divided by the summation of the resistance values, which is 1 plus 1, and then the main current 4 ampere. So it will be half into 4, that means 2 ampere. So this is the rule, current division rule. By applying that also we can find out the current value, and this will be useful when the resistors are not having the same value or equal value. Now this is the current value 2 ampere, and that will be flowing downward through this 1 ohm resistor. Next, in the next step, what we will do, we will consider this voltage source in the circuit, and we will deactivate this current source. And what is the rule of deactivation and independent current source? We will simply open that path, since here the current source is ideal current source. So that we will see in the, we'll see next. Now in this circuit, now we have considered this voltage source and we have deactivated the current source. Simply we have opened those terminals between which the current source was connected. Now here we can again, through this 1 ohm resistor, we want to find out the current value. This time we are assuming that this current value is I2, so we have to find out that value. Now here what we can see that this 2 ohm resistor is connected across this 6 volt voltage source. So across this 2 ohm, the 6 volt will be dropped. So this is really the voltage value, and between these 2 points A and B, no, this was A, this was B in the original circuit, and this was C. So between C and B, this voltage source is connected, 6 volt. So between C and B, the total voltage which will be dropped, that will have the value 6 volt. So VCB basically will have the value 6 volt, and VCB is nothing but VCA plus VAB, and we want to find out the current value. So if we can, this way we can, if we can find out the voltage drop across AB, then by the help of that value we can easily find out the current value. So VCA plus VAB will be 6 volt. And how we can find out the voltage drop across these two terminals AB? We can apply the voltage division rule here. Now we want to find out voltage drop across this. So the VAB, this time it will be that resistance value, that means 1 ohm divided by summation of both the resistances. So 1 plus 2 multiplied by the main voltage value, which is 6 volts. So it will be 1 by 3 into 6, that means 2 volt. So voltage drop across these two terminals is 2 volt, and the resistance value is 1 ohm. So the current value I2 will be, simply it will obey Ohm's law, and that will be V divided by R. So it will be simply 2 divided by the resistance value, which is 1, that means 2 ampere. And since this is the positive terminal of this voltage source, so current will flow in this direction through this path. So here the direction of I2 will be again downward. So in this circuit, for 4 ampere current source, the value of current which was flowing through this 1 ohm resistor, that has value 2 ampere, and that is flowing in downward direction. And for the voltage source, the current is also 2 ampere, and that is also flowing in the downward direction, flowing downward. So in both the cases, the direction of current is the same. So in this case, the net current, when we will find out, it will be simply summation of I1 and I2. So it will be 2 plus 2, 4 ampere, and the net current will also flow through that 1 ohm resistor in this direction. Thank you.